Alright, so as mentioned before, the variance is what we call the score of variation, right? And how we calculated it previously using the experimental approach. So the experimental approach was to take the sum of all of the individual values that we can observe from the experiment, and then we minus away the mean value, and then we square it, and then we divide by the total number of values. Now for a discrete random variable, this context over here would be in the theoretical approach, right? Because for a discrete random variable, when you draw out the probability distribution table, right, all of those are theoretically possible values that it could take on, right? They are not the final values that it takes on, but theoretically speaking, those are the values that it could take on. So how do we calculate the variance of a discrete random variable? So the notation would be like that: variance of a discrete random variable. So the whole idea behind it is trying to figure out what is the expected, or rather what is the value, what is the variance value that we can expect over here, right? Given that this is a theoretical approach. So this is a theoretical approach, that means we cannot say for sure what is the variance, but we can hypothesize, or rather we can put an expectation for what it is going to be. So the variance is the expected value when we take the individual values, minus away the mean value, and then we square it, right? So you can see that there's a lot of similarities between these two. And I'm just going to say it one more time. So the variance is the expected value that we can expect from the theoretical approach when we take each individual value that the discrete random variable could take on, minus away the mean score to get the difference, and then we square it, right? So when we perform this whole process over here for each of the x values, and then we find the expected value of this whole thing, that will give us the variance of x that we could expect, given that this is a theoretical approach. That means every single thing that we do here is all just theoretically speaking, right? It's not the experimental approach because there's no actual results. So with this, right, with this formula over here, we can then further simplify this to give us e bracket x squared minus e x over here, right? We can split this, and I'm going to show you how we actually split this later on, and which is going to be very helpful for you in the long run, basically. So the key thing here to remember is just this. You just need to remember this, and once you remember this, you are actually very good to go already. But before we actually do that, I think it's best for me to just show you all how this whole e bracket x minus the mean square can be written in many different ways, right? And which way you choose to write it depends on what you have in the context of the question itself. So this one can be expressed using the summation formula, which is the sum of all x minus the mean square multiplied by the individual probability, right? This is one way of writing it. Another way of writing it is by simplifying it to get ex squared minus ex, which is basically just x squared minus the mean score, right? Because at the end of the day, ex is just the expected value in the long run, or the expected average value in the long run, which is the average. So therefore, it's the average, right? And there are useful properties for this over here that I will go through later on, okay? But this one should be relatively straightforward because it's what we discussed earlier on, where you treat this as a function of x. So this is the function of the x, and then you multiply it with its corresponding probability, right? And then you sum all them up together. The other one will be this, which I will show you how we actually derive this. So starting from x minus u bar u squared, right? We know that this, when we expand this using your a minus b squared, you get a squared minus 2ab plus b squared over here, right? When you expand out this whole thing, right? And then from here, you can actually split it. So when you split it, you get e x squared minus 2ex, or rather 2uex plus eu squared, right? And then note over here that this mean, right, this is a specific value. So in other words, this is a constant, right? And then from the earlier sections, we know that when we have an expectation of a constant, right, this is just the value of u squared, right? And then over here, ex can be written as u as well. So when I simplify this, I get x squared minus 2u times u plus u squared, right? Because expectation of u squared is just u squared itself. I'm just saying u, but we all know it's not u, okay? It's just a symbol. It looks like a u. So when I simplify this, I get x squared minus 2u squared plus u squared over here, right? And then from here onwards, it just gives us a very nice value of x squared minus u squared, and that's the final answer over here, right? And then, oh wait, apologies, over here I forgot to put the square over here. Yeah, so there's a square over there. Yeah, so that is how we actually derive the formula over here. You don't need to prove this in the exams. You definitely do not have to. So all you need to do is to just remember this or remember this. Okay, and these things over here are what we call our variance of x. So you can see that variance of x links back to the concept of expectation again. So one way or another, you will always bump into the concept of expectation throughout this whole entire chapter. So it's just some useful properties. The variance of a constant, again, will always be 0. Because when you have a constant, right, the constant is the mean value, essentially. So when you only have one value, there's no variance, so to speak, because there's no deviation from that one value itself. So the variance of a constant is always 0. So don't mix it up with expectation, right? The variance of a constant is 0. You just repeat this to yourself a couple of times and then you remember it already. Now, the variance of a linear function, right? Remember that for variance, we will always square to exaggerate the differences. So we will basically square the scalar multiple, right? So with a, we will square it because we will square the whole thing, and therefore a will get squared as well. So here will be variance x. And then the plus b over here, since it's a constant that is separated from the ax, it just disappears, right? Because it's just 0 lah. Because the b, it does not affect it at all. And then later on over here, if we have variance ax plus by, it will just be a square variance x plus b square variance y. Okay, so right now it might seem all very abstract to you, these three very important properties as well as the two formulas that I went through earlier. But once we start applying them to the questions, I promise it will make a lot more sense. Okay, so feel free to watch this video as many times as you need. If not, please proceed down to this question over here. Pause this video to try this question out, and once you're ready, come back, resume the video, and let's break down this question together. Alright, so starting off with the first one, variance of x. So since we have the table of values over here already, let's just straight away use the values, right? So variance of x over here will be, you can define it as taking the ex minus the mean squared, which is essentially just x squared minus the mean, or mean score over here. So let's first calculate what is ex. From the table over here, this result of ex will be very useful for us in the long run. So ex will just be 1 times 0.4 plus 2 times 0.2 plus 3 times 0.1 plus 4 times 0.3, right? We'll use this many different times. So what's the expected value of x in the long run? And we get a value of 2.3 over here. Now how about ex squared? Right, what's the expectation of ex squared? So that is where you just extend the table that you have earlier on. So here, just going to draw the table here and then calculate x squared. So this will be 1, 4, 9, 16, right? So the expectation of ex squared will be 1 times 0.4 plus 4 times 0.2 plus 9 times 0.1 plus 16 times 0.3 over here. So in the end here, I get 1 times 0.4 plus 4 times 0.2 plus 9 times 0.1 plus 16 times 0.3, right? And I get a value of 6.9 over here, 6.9. So therefore, the expectation, right? What is the expectation over here? Apologies, I forgot to put the square over here again. Yeah, so there's a square over here. So in the end, for part A, right, it's just taking my 6.9 minus 2.3 and then I square it, right? Because remember earlier on when we expanded it over here, right, there is a square over here, and this essentially, this portion over here is essentially your ex. Yeah, so now back to here, we just need to punch this whole thing into our calculator and we will get a final value of 1.61, right? And that's the answer to this portion over here, right? Now for double I, same thing, but we need to use the important properties that we have learned earlier on. So for double I, when we want to find the variance of 3x over here, it's just 3 square variance x, right? Because when we square it, when we want to find the variance, we typically square it to exaggerate the difference and also to get rid of any negative signs. So we take 9 times variance x, which is 1.61 over here, right, from the previous answer over here, and eventually we get 14.49 as the final answer for double I. Now for triple I, when we want to find the variance of a constant 2, right, immediately we know it's 0, because when it's a constant, the difference or the effective distance between the constant and the mean value, which is the constant, is 0. Now last but not least, we have IV, so variance of 3x minus 2. How do we find that value? This over here, remember, any constant over here that is separate is not going to affect the variance, right? It will actually become 0. So this is effectively the same thing as just 3 square variance x plus 0. And then here is just 9 variance x, right? Which is the same answer as this. So therefore we get 14.49 once again. Okay, so this is how we actually derive all the important values over here. Apologies earlier on for my oversight on this. There's a square over here. Otherwise, the rest of the other questions are more or less like that. Okay, so feel free to let me know if you've got any other questions in the comments below. Otherwise, I'll see you in the next video for the next concept.